Okay, welcome back everybody. This is the second video with the new technology, so I'm not sure I've got everything sorted out, but I did figure out that I want to have more colored pens next to me when I'm doing this because I don't like just doing it all one color. So I've got a few pens all ready for me to go now. Okay, so this is a video that is following up on us working on both stoichiometry and gas laws. So the previous video was just looking at some stoichiometry, and now we're going to do a stoichiometry and gas law problem. So when we have stoichiometry and gas law problems, again, just like before, well, I guess not just like before, one of the things that we're going to need to have involved with these problems is that we have to have some kind of gas. And you could have a gaseous reactant, you could have gaseous products, you could have some of each. And there are some of those on our smart work. So in this problem, we're going to have a scenario where we've collected a certain amount of this gas and we know about how much we have, and we're going to ask about some of our reactants or some of our other products here. So in this problem, I'm going to say we have collected hydrogen gas in a 50-liter container kept at 2.75 bar and 300 Kelvin. Great. So our question is, what was the concentration of the HNO3 if we used 237 milliliters to dissolve the iron? Okay, so just like before, when we do our stoichiometry problems, we always want to think about what is the A and what is the B. So what is the thing that we know a lot of stuff about, and what is the thing that we are asking about? So when you look at this problem, hopefully you can identify that when we say what was the concentration of the HNO3, this is telling us that the HNO3 is the B. And when we look at the rest of the problem, it looks like we said something about iron, but we don't have any numbers here. And so we collected the hydrogen, and we know quite a bit of information about it. And so this implies to us that the hydrogen is the A in this problem. Okay? So that's our first step when we're doing stoichiometry problems, is just to orient ourselves with what is A and what is B. The second step that we're going to use here is to figure out where are we on this chart, or where do we need to be. Now, of course, I made this a little bit tricky because it's a gas law problem and I didn't put anything about the gas law stuff on our diagram here. But we're just going to go to our foundational idea that we need to get to moles of A. Okay? And the reason why I didn't put the gas law on here is because you can come at the gas law from a lot of different ways, and so it would just make this a very cluttered diagram. So I guess I could put a little bubble that said something like volume, pressure, and temperature of A, and then we're going to go using the gas law. Okay. So our first goal is just to calculate what the moles are, right? So our gas law, we're going to use the ideal gas law, and we know that that's PV equals nRT. So when we look at this problem, we can identify what pieces of information we have been given here. So just like we said a moment ago, we can see that this is the volume, this is the pressure, and this is the temperature. And I verify it's already in Kelvin, so I don't need to do that unit conversion. Okay, so our next step is going to be to convert this equation into one that is giving us the variable that we need. And so we look, we've got a p, we've got a v, r is a constant, so we'll look it up. We've got t, we're going to solve for n. So we do this by dividing out the r and the t from both sides. These will cancel over here, and we will get p times v divided by r times t. So let's plug those in. And if you want to pause the video while I do this and do this on your own, that's a great idea. And then you can come back and check your work. So go ahead and do that. I'm going to keep writing. R values we need to look up. We have bar, so we're going to use 0.083145 liter bar over mole Kelvin. And that's multiplied by 300K. And while I'm writing this number out and kind of detailing it here, I'm going to mention that you noticed that I put a little period right here and also right here when I wrote this down. This is to tell you that all three of those digits are significant, so that we do have 3 sig figs. So this is one of the ways that we communicate that kind of information. Okay, so now let's just pull out a calculator and put those numbers in. So I'm just using my cell phone because that's what I had handy. So notice that here I've multiplied these two numbers together. I can do this all in a string. I'm now going to divide out 0.083145, and then the 300 is also on the bottom, so I need to divide that out as well. I don't need parentheses here. I could do it with parentheses, and if you want to see that, I'm happy to show it to you that way as well. Just let me know. Okay, so I see that I've got 3 significant digits for the bar and the volume and also the temperature, so I'm going to keep 3 significant digits. That's 5.51 moles of hydrogen that we have generated. All right, so this has gotten us to the first step in our problem. So now we are right here. We've used the ideal gas law to calculate the moles of A. Now we are going to plan out the rest of where we're going to go. And so this is usually what I do before I get started, is I identify my starting place and then I identify my ending place. So if we go back here for a moment, we were going to solve for the concentration of the nitric acid. And the concentration is over here, that's this capital M. So that means we actually are going to need the moles, and we already have the volume. So I'm just going to write this on the side here as a reminder that molarity is equal to, and if this is, we're talking about B, this is the moles of B divided by the volume of B. And it will be, of course, in a solution. And it will be different from this gas because it's not going to be a gas, right? This is a solution, that means it is aqueous. And so when we looked at our problem up here, this is aqueous, so we know we can't use the ideal gas law even though there's volume here. We instead need to use molarity, and that's how we're going to get moles per liter. We're going to use that piece of information to get us all the way there. Okay, so our first step after we've identified where we're going is to use our mole ratio. So let's write out our moles of H2 again, 5.51 moles of H2. The mole ratio is from the balanced equation. So I have 1 mole of hydrogen and 2 moles of HNO3. So I'm going to write in a ratio. 1 moles of H2 goes on the bottom, and 2 moles of HNO3 go on the top. And I'm not actually going to write a long string of any calculations here. I'm just going to multiply 5.51 times 2. So when I do that, that's going to give me 11.0 moles of HNO3. Okay. Now, as I said right here, molarity is moles over liters. So I have moles, and I also know what kind of liters I used, or rather, excuse me, here, let's go over here. I have milliliters instead of liters, and I have moles. But because I have moles, these moles of HNO3 were in the solution that we used. So we can simply divide our moles divided by our liters. Right now we have milliliters, but we're going to convert that. And there are 1,000 milliliters in a liter. So as we are doing this calculation, we will functionally multiply by 1,000. So we're going to multiply by 1,000 and then divide by 237. And then we get a crazy concentration, 46.5 molar HNO3, which we can't actually do. And this is what happens when I write a problem on the fly. Sometimes the numbers turn out a little weird. So I kind of knew I was making this too concentrated anyway. But the math works fine here. Okay? So just to quickly review, what we did here for our process was we identify the A and the B, and we do this by looking at the original problem and seeing that the A is the step where we have lots of information, and the B is the thing where we are asking about it. This is where we have to find the information. Okay, so that was our first step. And then we identify what our starting place is, or rather what path we can use to get moles of A. All right, so really that's our bottom line. How do we get moles of A? Sometimes it's a short step, sometimes it's a longer one. So then we go from moles of A to moles of B. That's what we did right here. And then our final step is to use the moles of B to find the answer, whatever they were asking in the problem. Right? So hopefully this is a sufficient review on using gas law stoichiometry. I'm probably going to create one more short video with a more complicated gas law problem, just stoichiometrically, fewer ones and stuff, and more different numbers that you can use as an extra practice, or maybe I'll just post it as a challenge problem. All right, I hope this worked out really well for you, and that you let me know any editing feedback for future videos. Thank you.